Now let us continue from where we left in our previous class. I hope all of you remember we have started discussing with cube. We discussed several parameters in cubes like total surface area of a cube is 6a square, volume of a cube is a cube, and then we derived the diagonal of a cube as a root 3. Now let us continue forward, sir. Now the main important thing, yes, you can easily remember what is the total surface area, what is the lateral surface area, what is the volume of a cube, what is the diagonal of a cube. All these things are very fine, sir. This is something which is not haunting any student. These are some of the very easy ways of remembering, and you can remember them very easily. It's not a big deal of remembering those formulas or probably the notations or whatever it is. But the main important thing in this particular topic, not only in cubes I am talking about, but it can be in any of the three-dimensional figures. But right now let me concentrate on teaching you on cubes. The main important thing is that we need to learn how to cut the cube. The main important thing is we need to learn is all about cutting the cube. That is something which is very important for all the students. Now please listen carefully. We shall discuss 3 cases in this. I will teach you very easily how you can visualize with all these 3 cases. I have already told you, sir, I am not physically visible in this particular session, so it is difficult for me to explain little bit also, because I cannot show you with a book or any other three-dimensional figure. But having said that, my explanation probably should make you visualize whatever I am trying to say you here. Now please listen carefully, sir. We shall discuss 3 cases in this. Now case number 1. For all the 3 cases, I will have to write the diagram. So please have little patience before you conclude something. Listen carefully, sir. Case number 1. First, let me write the diagram of a cube and then tell you what is the case number 1. Then tell you what is case number 1. Now see here. First, let me write the diagram. Again, I am saying you diagram is not drawn to the scale. This is a cube, right? This is a cube. Definitely do not look like a cube, because length, width and height are not same in the diagram whatever I have written. But please consider this as a cube for time being. Now see here, sir. This is the cube. My first case is, I already told, the main important thing that we are going to discuss is how to cut the cube. How is the learning is all about the cutting the cube here in this case, in all the 3 cases. The first important thing what we are doing is cutting a cube from all the vertices, right? Cutting a cube from all the vertices. That means we already know that totally there are 8 vertices. Totally there are 8 vertices in a cube. My whole agenda is how to cut a small cube from all of these 8 vertices. Let me mark those 8 vertices. This is one of them. This is the second one. This will be my third one. This is the 4th vertex I am talking about. This is the 5th vertex. This is the 6th one. And these are the another 2 vertices, right? These are other 2 vertices. Totally I have 8 vertices in a cube. What I will do is, first of all, let me mark all these things. Let the side of the original cube be A, right? The side of the original cube be A. There are 8 vertices in a cube. Let us draw a small cube. Like this. Suppose, for example, let me draw a small cube like this. Let us draw a small cube like this of side B on each corner or each vertices of the given cube. That means on each of the vertices I will draw a small cube of side B. This is side B, this is again side B, something like that. On each of this, on this vertices also I should draw a small cube. This also I should draw, this also I should draw. But because it is a cube where length, width and height are all same, I am drawing it in one vertex and I am trying to correlate with all the remaining vertices as well, right? I have just drawn a small cube of side B in one of the vertex for time being. Multiply it by total number of vertices, which is nothing but 8 in a cube. We will get the total something which we are aspiring for. Now if I draw a small vertex like this on one of the vertices, and if I want to cut it, if I want to cut it, now my whole agenda is I want to find the total surface area of the remaining solid. Listen to this carefully, sir. If you understand case 1 properly, I believe that case 2 and case 3 will be pretty easy for you to analyze. I want to find the total surface area of the remaining solid. Now, before moving on to remaining solid, first of all, what is the total surface area of the original bigger cube? Original bigger cube is having a side of A. So the total surface area of the original bigger cube is, it is 6 times of A square, right? It is 6 times of A square. Now think logically, listen to this carefully. Suppose if I remove a small cube from each vertex, this is one of the vertex I have considered right now. Suppose if I remove a small cube, this is the small cube I am referring to. If I remove a small cube from each vertex, then what will happen? Then if you observe carefully, I will lose 3 surfaces from the original cube. From this original bigger cube, I will lose 3 surfaces. Let me mark them also for your better understanding. I will lose 3 surfaces from the original cube. That means this upper portion I will lose it, this left portion and this portion I will lose it, because I am cutting the small cube from the original cube. I will lose 3 surfaces from the original cube. But if I remove the cube from corner, how many surface will it touch? If I remove the cube from a corner is nothing but the vertex, how many surface will it touch? It will touch 3 surfaces. That is what I have marked. This is one of the surface, this is the other surface, this is the other surface. Totally it will touch 3 surfaces. So if I cut and remove, I will lose 3 surfaces. B square area of square. That means this side, the side of the smaller cube, I have called it as B. So the area of that is B square, right? Area of that will become B square. So if I cut and remove, I will totally lose how many surfaces, sir? 3 surfaces. I have marked it in red color. I will totally lose 3 surfaces of area B square, which is nothing but a square. But if you observe internally carefully, if you visualize it in a 3D format, if you observe carefully internally, 3 more squares will be created. How will the 3 squares will be created? 3 more squares will be created because, think logically, for a cube totally there are 6 faces. 6 surfaces will be there for a cube. So if I remove from one vertex, if I remove a cube, I will totally lose 3 surfaces. The 3 marked surfaces I will remove. The behind of is internally there will be 3 more surfaces which will be created, or in other language 3 more squares will be created. Therefore the total number of area under loss, that means 3 losses are happening, and the total number of areas which are created, that means 3 areas are created, they both are same. That means, can I say that the number of losses which is happening and the number of area of square which is getting created internally, they both are same. That same is nothing but 3 each in this case. So in simple language, the difference between the loss happening and the creations happening, it is 0. 3 minus 3 is 0, or in other simple language, there is no profit in this case which is there, right? There is no profit happening in this case. I hope you are understanding. So the total surface area of the remaining solid, it is nothing but equal to, let me write it here, total surface area of remaining solid. Initially it was total surface area of the original bigger cube, that is 6a square, plus something. That something we understood just now, that there is no profit which is happening in this case, because three surfaces are removed or it is taken outside after cutting, but internally another three surfaces are getting created, because totally a cube will have 6 surfaces. So 3 minus 3, the difference is 0, or the profit is nothing in this case. So total surface area of the remaining solid is 6a square plus 0. It is nothing but 6a square itself. There is no loss which is occurring in case 1. If you cut a cube from all the vertices, I am talking here about only one vertex. One vertex is giving you a loss of 0. So 8 vertex will also give you a loss of 8 into 0, which is nothing but once again 0, sir. So total surface area of the remaining solid, it is equal to the total surface area of the original cube. So in this case, whenever you are cutting a small cube from each of the vertex, you will not have any loss. That means if you visualize in 3-dimensional, 3 surfaces will be lost in original cube, but inside I am talking about same to same, you will have 3 surfaces of b square area created. So no area is lost as a resultant in this case. I hope first case is very clear for every student who is listening to the class. First case is cutting a smaller cube from all the vertices, right? From all the vertices. Totally how many vertices, sir? 8 vertices. So it makes no difference. Now let us move on to the second case of this beautiful concept. Case 2. Now we already learnt how to cut a small cube from each vertices. Now let us concentrate on cutting a cube from each edge, right? We will also see what happens if we cut a cube from each of the edges. We already have seen in case 1 what happens if we cut a cube from each of the vertices. There is no loss, there is no change in fact. So if it is cutting from each of the edge, what will happen? That is what we are going to learn right now. Now before that let us draw the diagram, sir. Give me a minute, let me draw the diagram. Assume this as a cube. Okay, sir. Now see here. Listen to this carefully. I will call the side of the original cube as A. Now, we all know that how many edges will be there in a cube? There will be a total of 12 edges in a cube. Now, the question is, from each edge, we shall remove a small cube, right? We shall remove a small cube. Let me write it. Now, from each edge, we shall remove a small cube. Now, suppose for example, if I draw a small cube like this, right? If I draw a small cube like this, so this will be the small cube. Suppose for example, I am not that great in drawing the diagrams, sir. Suppose, okay, beautiful. Okay, now see here, that is one of the edge which I have considered. I have drawn a small cube. Let us take the side of the smaller cube as x units in this case, instead of taking it as what do you say, in the previous case what did we take, sir? In the previous case we took it as b. Now I am taking it as x for the smaller cube. That's the only difference, sir. Now from each edge we shall remove a small cube of side x. Now what will be the total surface area of the remaining cube? First of all, if I remove a small cube from each edge, what will be the total surface area of the remaining cube? Let us write it. Total surface area of the remaining cube will be how much? Now first of all, total surface area of the entire cube is nothing but we already know it as 6a square. Now plus what will happen right now? Let us visualize it, sir. Now suppose if the small cube is removed from the edge. If this red color small cube of side x is removed from the edge, then the cube will be touching how many surfaces? How many surfaces will this cube be touching in that case? It will be touching two surfaces. Which are those two surfaces? One is the upper surface and the other one is the side surface. Now if you cannot visualize what I am trying to say, very simple sir, take a book right now. Take a book right now in your hand, and if I place a small cube, I should place and remove a small cube on the edges of the book, because the second case I am talking about the edge. On the edges of the book, I should place a small cube of side y. Side can be anything, in fact the side x here is what I am talking about. It will touch two surfaces. You can visualize it if you have a book right now in your hand. If you have a cube also, it will be very easy to visualize it. If you put a small cube and place it on one of the edges, it will be touching two surfaces. One is the top surface or the upper surface, and the other one is the next side which is closer to that particular surface, right? So if I remove that, totally how many surfaces we will be losing? We will be losing two surfaces. The surfaces whichever it is touching, those two surfaces we will be losing it. So we will be losing two surfaces. That means totally there are 6 surfaces for a cube. Out of that, if I remove that smaller cube, I will be losing two surfaces. That means that inside totally 4 surfaces are created. Inside totally 4 surfaces are created. Let me mark it in this diagram also, sir. So that means here this left side will be created, this left one will be created, this right one will be created, this backward one will be created, and then this bottom one will be created. Out of totally 6 surfaces, the 2 surfaces which are touching the edge, if they are removed, another 4 surfaces will be created. I am talking and I am more interested about how many are created. Totally 2 are lost, and how many are created? 4 surfaces are created. That means I have a loss of 2 surfaces. And totally 4 more surfaces are created internally. Now what is the difference between these two? The difference between these two is, that means if I compared how much is created compared to the loss, there is 2 extra which is created. That means the profit between these two, or the difference between these two, it is how much, sir? There are 2 more extra squares which are created internally. Each surface is of x square, right? Each surface, the area of each surface, it is nothing but x square, because everything is side x in the smaller cube. If each surface is x square, so 2 extra surfaces are created. 4 minus 2, the difference is 2. That extra is what I am saying it as 2. I hope everyone is able to visualize. For one surface it is x square. So for 2 surfaces, for 2 extra surfaces, it is 2x square. Now this is the total surface area of the ones which are extra created. For it is, that means total surface area of the remaining cube is 6a square plus 2x square. But think logically, sir, this 2x square is for one edge. It is for only one edge. But totally how many edges are there in a cube? Totally like that there are 12 edges. For one edge it is 2x square. For 12 edges it is 12 into 2x square. So very important point. Total surface area of the remaining cube in case 2, where you are cutting a cube from each edge, it is nothing but 6a square plus 12 into 2x square, where a is nothing but the side of the bigger cube and x is nothing but the side of the smaller cube. I hope you are able to visualize it very clearly. Now there are 2 terminologies which we have already taken care of. One of the terminology is vertex, other property or the terminology is edge, and the remaining terminology what it is, sir, it should be face. Now the last case what we will be discussing here is in terms of cutting. We will be discussing the last case saying as cutting a small cube, from each face. From each of the face I need to cut a small cube. What will be the total surface area of the remaining solid or the cube? That is what I am discussing in case 3. Now try to visualize it, sir. Again, this becomes very easy if you have understood case 1 and case 2. I am drawing a cube right now. The side of the cube is A, right? The side of the cube is A. Now the case what I am discussing is cutting a cube from each face. Now let me draw it in a different color for our better understanding. This is one of the face. What I am hovering right now, this is one of the face. Now I will draw a small cube. I will draw a small cube here. So this cube, let us call the side of this cube as y, right? Let us call the side of this cube as y. I totally have, first of all, how many faces will be there for a cube? There will be a total of 6 faces. Now I am cutting a small cube of side y from each of the faces. I am interested in finding total surface area of the remaining solid. Right, I am interested in finding total surface area of the remaining solid. Now we already know that total surface area of the bigger cube is nothing but 6a square plus it should be something else. What is that something else? We will visualize it right now. Now think logically, sir. From each of the 6 faces, I want to cut a small cube of side y. Now suppose for example, again take a book. If I take a book and place a small cube on one face, suppose for example you are keeping a small cube on one of the face. One of the face is nothing but your, what do you say, like binding of that particular book. I hope you are able to visualize. Totally there are 6 faces in a book. One of the face is the binding, right? The first starting binding, and you can also keep it at the bottom binding also, whichever. Totally there are 6 cubes basically, 6 faces basically. I am talking about one of the face. One of the face is binding, the top binding. On that top binding, you please place a small cube right now, right? Visualize it, sir. Visualize it. It's more, geometry is all about visualizing. Geometry mensuration, it's all about visualizing. I am placing a small cube of side y on one of the top binding. That means, can I say that I will cut it? I am only touching one surface right now. Totally I have totally 6 surfaces. Surfaces is what I meant as faces. Both are same, right? Totally in that particular book there are 6 surfaces. One of the surface is only what I am touching with the smaller cube. That means that surfaces I am losing it. I am losing the area of one surface out of 6 surfaces. But internally I am creating 5 surfaces. I hope you are able to visualize it. Totally 6 surfaces are there for a cube. I am losing the area of only one surface. But internally I am able to create 5 surfaces. That means I am losing one and I am creating 5. What is the difference between 5 and 1? The difference between 5 and 1 is it is 4. That means I am able to create, compared to the losses, I am able to create 4 more surfaces of squares. That means the profit is 4 squares, right? 4 squares I am able to do it extra. That is the profit. Area of each square of side y, it is y square. Area of each square of side y is y square. Like that I am able to create 4 extra squares. So this will be 4y square. Now this 4y square is the area for one face. But in a cube I will be totally having 6 faces. So this should be multiplied by 6. So the total surface area of the remaining solid is how much? It is 6a square plus 6 into 4y square. I hope all the three cases whatever we discussed should be very clear. A quick recap of what we have discussed. Cutting a cube from all the vertices, three surfaces are taken out, that means it is removed. Three more are internally built created, that means 3 minus 3 I am not creating anything extra, so it is profit of 0. 0 into 8 vertices is 0, so total surface area of the remaining solid still remains the same. There is no loss in case number 1. Case number 2 is cutting a cube from each of the 12 edges, that means in one edge I am able to create. So first of all I am losing two surfaces in one edge, so that means 4 more are created. So totally compared to the loss I am having 2 extra. 4 minus 2, the difference is 2, that means the profit is 2. For one surface the area is x square. For 2 extra surfaces the area is 2x square. This 2x square is only for one surface, one edge. Like that I have 12 edges. So it is 2x square multiplied by 12. That means the total surface area of the remaining solid is 2x square multiplied by 12 plus the original area 6a square. This should be the case 2. And the final case is cutting a cube from each face. Each face it is of it. If I place a small cube of side y units on one of the face of a book or a cuboid or a cube, whatever it is, one surface is lost. 5 surfaces are created. The difference is 4. For one surface it is y square area. For 4 surfaces it is 4 into y square area. But that is for only one face. One face. Totally there are 6 faces in a cube. Multiply 4y square by 6. And then the original area of 6a square will anyway be there. I hope case A, cutting a cube from a vertex, cutting a cube from all the edges, cutting a cube from each of the face. All the three cases should be very clear for you people before we move on to any problems based on any of the geometrical figure. I hope it is clear for you, sir.